we would like to use the definition of limit to show that the limit as z approaches z0 of z bar is equal to z0 bar. So the definition of limit says that the limit as z approaches z0 of f of z is equal to some number L if the following condition holds. Given any number epsilon greater than 0, a small positive number, there exists a corresponding number delta, also positive, such that if z is within delta units of z0, z minus z0 is less than delta, and also we have to say bigger than 0 because in this limit z is approaching z0 but not equal to it. So the distance between z and z0 needs to be positive. But if the distance between z and z0 is small, if it's less than this number delta, then the distance between f of z and L is less than the prescribed tolerance epsilon. F of z minus L is less than epsilon. So we can think of epsilon as being a tolerance and delta as being a threshold. So that in a limit, we want to say that as z gets close to z0, then f of z gets close to L. And we want f of z to get as close to L as we want. So that'll be our tolerance. We prescribe a tolerance, and then we have to show that if z is sufficiently close to z0, if z minus z0 is less than this threshold, then indeed the tolerance condition is satisfied. Okay, so for this particular example, to show that given any epsilon, given any epsilon greater than 0, there exists a delta such that this happens, we will need two facts. One is that for any complex number, w, the modulus of w bar, is equal to the modulus of w. This is pretty obvious. The complex numbers a plus bi and a minus bi have the same modulus, which is the square root of a squared plus b squared, because the minus here gets squared, so you end up with the same modulus. And second, we're going to need the modulus of a difference. We're going to need the conjugate of a difference is the difference of the conjugates, not the modulus. The conjugate of a difference is the difference of the conjugates. And actually, I think we're going to be using it this way. So we're going to have a difference of conjugates, and we're going to want to say that that's the conjugate of the difference. So we'll need these two basic facts. All right, so here we go. We want to show this. So we're going to let epsilon be greater than 0. And we want to find a delta greater than 0 such that if z minus z0 is less than the delta and bigger than 0, then the z bar minus z0 bar is less than epsilon. So we should analyze this condition, this tolerance condition here. The modulus of z bar minus z0 bar is equal to the modulus of z minus z0 quantity bar, using condition number 2 here from right to left. Here we have a difference of conjugates, and that's the conjugate of the difference. And now we have the modulus of the conjugate of a number, and so we can use condition 1, and this is just equal to the modulus of z minus z0. So if we want to find a delta that will make this difference less than epsilon, we can just choose the delta equal to epsilon, because this quantity here and this quantity here are equal. So we're going to let delta equal epsilon. Then if z minus z0 is less than delta and bigger than 0, then we have the modulus of z bar minus z0 bar, which is equal to the modulus of z minus z0, as we've just shown here. And that's less than delta, but delta is equal to epsilon. And so we have it. The modulus of this difference is less than epsilon. So we have shown that this condition is satisfied with delta equals epsilon.